Okay. So this is my first time giving a hybrid Zoom talk in person. So this is an interesting experience. And is there? I did pull up this pointer here, but I don't. I'm sorry. I'm going to use my pointer this way instead of using my pointer on the screen. If you don't mind. Okay. So so I'm going to talk about a line of work that started with Sid Nagel and many years ago with Carl Goodrich, my graduate student, and then it was carried on by Jason Rocks with Yidi Pashin, his Sid student, Daniel Hexter, our joint postdoc, and culminating in recent work by Naki Stern, which led to a realization of this learning machine by Sam Dillaboo and Doug Durian, and that was really enabled by collaboration with Eleni Kadafori, my terrific colleague at Penn. So, so what I'm going to talk about today, before I get into what I'm going to talk about today, I'm going to have an advertisement. So I'm sorry, I'm going to begin and end my talk with ads. Should be able to. How do I advance with this thing? How do I? It's not working on this.
It's working on your computer.
Yeah, but no, when I do this, it doesn't advance. So how do I advance the next slide? This is really not like giving a Zoom talk at home. Oh, how did you do that?
You clicked on the.
There you go.
Okay, now it's working. Okay, great. It takes an experimentalist.
There you go.
Okay, so let me just say we just have this new Center for Soft and Living Matter at Penn, and really want students and postdocs to come and join us there and work with us. More than 60 faculty from more than 10 departments, about a dozen departments across campus, self-identify as working in soft and living matter. You know, our faculty are really great. We have wonderful colleagues there. So I encourage you to come and join us in the fun. Okay, so we want to teach materials how to function, right? So what functions do we have in mind? So I'm going to focus on two in this talk. So let me talk about the first one is just Poisson ratio, really simple property. So the idea is the following: the Poisson ratio dictates what happens if you take a system and you, for example, stretch it this way, right? Is it going to stretch out in this direction in the orthogonal directions, or is it going to get smaller? So a rubber band, right? You stretch it out this way, it gets there that way. That's a positive Poisson ratio. If you stretch it out this way and it gets bigger, it stretches out also in the orthogonal directions. That's a negative Poisson ratio. And its linear response is directly related to the ratio of the shear to bulk modulus. Okay. What got us started with this was thinking about jam packings, which obsessed Sid and me for maybe 15 years. So the idea was that what we knew about jam packings was that the ratio of the shear to bulk modulus is very tunable, okay, but not tunable to negative Poisson ratios. You can basically tune from Poisson ratio of 0 up to its maximum value, okay, or yeah, so or near 0 to up to its maximum value. So it's a lot more tunable, and let me explain that first. Why? So let me first describe what jamming is. Okay, so jamming is what happens if you take a bunch of particles, say spheres, that have a repulsion when they overlap. Okay, no interaction when they don't overlap. If you look at the system at 0 temperature, you're looking at what happens at an energy minimum. And what you find is that at a low enough density, right, the particles can kind of find an arrangement where none of them are overlapping and the energy is 0. But if you go to a high enough density of particles, you get unavoidable overlaps, and these are the forces of repulsion between them. So that's explaining this in physics terms. Let me now explain it the way a computer scientist would do it. And you'll see why later in the talk, why it's useful to think about jamming it this other way, which is to say, well, I've got a bunch of spheres and I want to put on constraints. I don't want any of them to overlap. Okay, so how am I going to enforce these constraints? Well, I'm going to construct a cost function, okay, which says that if there are overlaps, I pay a price. Okay, and then I'm going to minimize this cost function. I'm going to do gradient descent on it, okay, by adjusting some degrees of freedom, which in this case are the translational degrees of freedom of the particles. Okay, and if I am at a low enough density, I can satisfy all my constraints. Okay, if I'm at a high enough density, I can't satisfy all my constraints, and I end up at a local minimum of the cost function, which is just the energy. Okay, so it's a totally equivalent way of stating the problem, but now as a constraint satisfaction problem, and that's like the way you train a neural network. Okay, so what do I mean by the ratio, the shear to bulk modulus, the Poisson ratio being quite tunable for jam packing? The idea is if I take that same potential, okay, and in keeping with the idea of cost functions, you just usually put a quadratic cost. So the cost is just quadratic in the amount of overlap. Okay, that corresponds in physics language, right, to a harmonic repulsion. So if you have a bunch of spheres with that harmonic repulsion, the lowest energy state is the FCC crystal. If you put the system in an FCC crystal and you put this thing under pressure so that there are overlaps, okay, and now you lower the pressure, okay, you find that the ratio of the shear to bulk modulus is totally flat, okay, until you get to the point where they're just touching, and then if you go below that, both the shear and the bulk modulus vanish. If I look in the jam system, on the other hand, that ratio of the shear to bulk modulus, yeah, and feel free to interrupt and barge in either on Zoom or in person if you have a question. Yeah.
This is just repulsive interactions?
Just repulsive, and they're finite range, so there's no interaction beyond the diameter.
Why is there a shear modulus? Why can't I just pull the crystal apart? Like what would?
Because it's under pressure.
Okay.
Yeah, that's right. So yeah, so I'm imagining it, putting it under pressure and then just lowering that pressure towards zero. So yeah, in the jam case, then the ratio of the shear to bulk modulus goes continuously to zero at the jamming transition, which is where the pressure goes away, where the pressure vanishes, where they're just touching. Okay, and so you see right away here that this ratio, the shear to bulk modulus, and hence the Poisson ratio, is much more tunable for the jam case than for the crystal. So that was our starting point for starting to think about all of this. So now if we want to understand this better, right, it's helpful not to think about the jam packing itself, but to think about a system which in linear response is identical, which is to take my jam packing and put a node at the center of every particle and put a spring connecting every pair of overlapping particles or interacting particles. Okay. So here's my equivalent spring network. Okay, and so the ratio of the shear to bulk modulus is the same for these two systems. The shear and the bulk moduli are the same. Okay, and what you see now is lowering the pressure on the jam packing. As I lower the pressure, I lose contacts. Okay, so that means I'm losing springs. I'm losing these connections, these edges here. And so it's like pruning springs. It's like removing springs from this network. So what's the effect of removing springs? So it turns out that it's useful to think of the following. Let me just go into my network and grab spring I, bond I, and take it out and say, how much does that change the bulk modulus if I take it out? How much does it change the shear modulus? Okay, and if it's a crystal, right, how much it changes the bulk modulus is some series of delta functions depending on the complexity of your unit cell. Okay, so now if you add disorder, what you would expect, right, is that these delta functions would smooth out. So you get some peaks, but that's not what happens. It looks like this. Okay, has this shape. We understand this shape And it's a continuous distribution, okay, that stretches all the way down to 0. Not only that, we found that how much the bulk modulus changes for a given bond is totally uncorrelated with how much the shear modulus changes. So this got us thinking, and we thought, oh, we don't have to just remove the ones that would be removed under the jamming protocol of lowering the pressure. Let's imagine that we can go in and remove any bond we want. Okay, then suppose I wanted to have a negative Poisson ratio. Well, what I want is the ratio of the shear to bulk modulus to be bigger than the dimensionality divided by 2. So 3 halves in 3 dimensions. Okay, and how can I do that? Well, if I selectively prune, if I just prune randomly, it turns out that ratio stays totally fixed. As I prune my edges and I change the number of springs per node, that's delta Z here, minus 2 times the dimensionality. This is just flat if I prune randomly. But if I take this thing and instead of pruning randomly, I prune the bond that decreases the bulk modulus the most. That's doing gradient descent on the bulk modulus. Okay, then the bulk modulus decreases much faster than the shear modulus, and this ratio just shoots up. Okay, and remember that a 0 Poisson ratio, which of course is why cork has a Poisson ratio near 0, which is why it's useful for corking wine bottles. So that's above this dashed line. Okay, the Poisson ratio is negative. And when this ratio goes to infinity, the Poisson ratio goes to its maximally negative value of -1.
Sorry, Andrea,
Yeah,
is the optimal bond to break, is that the one that's automatic already under the most stress, or
very good question. It is very close to that. They're highly correlated. They're not identical necessarily. It's not quite the same. So it's even more efficient to remove the one that lowers the bulk modulus the most. But in fact, you could. What we originally did was to remove the one that was under the most stress, and that's really important. I'm gonna make a big song and dance about that. Yeah. Okay. So what we're doing, right, is our bulk modulus is our cost function now, and what we're doing is we're doing gradient descent on that cost function by changing what I'm going to call a learning degree of freedom. Right, which in the case of jamming, that learning degree of freedom were the translational positions of the particles, right? That's what I was allowed to vary in order to minimize my cost function. Here, right, my learning degrees of freedom, if I'm just removing bonds, it's either the presence or the absence of the bond. Okay, but I could do many other things. I could say, oh, I'm going to take this bond away from here and I'm going to stuff it in there. That's what your former colleague Mathieu Biart did, okay, in work that was done around the same time. Or I could vary the edge stiffnesses, okay, the spring constants, or I could vary the equilibrium lengths of the springs. I could vary any of these properties of these edges of my network and allow them to be my learning degrees of freedom. And I can see, wow, this is really general, okay? I can take any mechanical property that I want, okay, that can be written as a sum over the edges, okay, and then I can vary these learning degrees of freedom to do gradient descent to get that thing to have whatever value I want. Okay, so all I had to do to tune any mechanical property is construct the right cost function. So that's pretty powerful. So then we started being more ambitious. Okay, we decided to tune Alistair, and this is what I should have said. Mathieu was not tuning Poisson ratio, it's tuning Alistair around the same time that we were tuning Alistair.
So Andrea, there was a really distinct asterisk next to the.
Yes. The asterisk is that it has to be written as a sum over the edges.
Okay.
Yeah. Be able to be written as a sum over the edges. Okay. So so what is Alistair? So this is the next function that, so I was talking about tuning Poisson ratio. I'm now talking about tuning another thing, which is allosteric. Okay, so this is something that a lot of proteins have. Okay, and the idea is, for example, enzymes. So here's an enzyme, okay, that wants to make some chemical modification to this molecule over here. Okay, right now the enzyme is off. This molecule is not able to bind to the protein. But this enzyme has this regulatory molecule here that when it is bound over here, that opens up this binding pocket, and now this thing can somehow allows that to bind. Okay, so that's an example of, and this is allosteric, where I apply, if I think about it in physics terms, what I'm doing is I'm applying a strain here by binding this molecule, and that's creating a strain over here, a local strain, but at a distance, some distance away, okay, which is of the same order as this one. And you say, okay, elasticity, we know elasticity decays really slowly, it's long range, okay, but if you actually put in the numbers for a typical protein, the response that you would expect to see at this distance is down by a factor of 10 to the minus 2 or 10 to the minus 3. Okay, that to get a strain of order 1 in response to a strain of a strain here that's of order 1 compared to the strain there is special. Okay, so so that's what allostery is, and so we're talking about allostery in group meetings, and my colleague Eleni Kadafori said, oh, the brain vascular system does the same thing. Okay, so the idea is the following, that there's blood coming in through the arteries input, okay, the source, pressure drop, and the brain actually uses a huge fraction of the oxygen that comes into our bodies, 25% of it that comes in through the lungs. And it does that to support functions of the brain. So right now I'm talking, okay, and so my speech cortex needs extra oxygen. And so it increases, so what the brain is doing, the vascular system is dilating some vessels in this network, okay, of blood vessels, and it's contracting others. So it's changing their conductances in real time to direct more flow to my speech cortex. Okay, and so so that is the output. Okay, so again, I have a localized input, okay, at the source, the arteries, and I'm directing by varying the conductances in this case, not the spring constant, so the presence or absence of a spring. Okay, I'm varying the conductances of the vessels to get a localized pressure drop some distance away. Okay, so it's the same problem. I'm going to call that flow allostery. Okay, and in fact, the flow system and the mechanical flow network and the mechanical network have very similar mathematics. And the way to see that is that, in the mechanical network, right, the nodes adjust their positions so that the energy is at a minimum, and I have force balance on every node. In the flow network, the currents adjust to minimize the power and power loss, and the current at every node is their net current at every node is their Kirchhoff's law. Yeah.
Okay, I'm a little confused. Maybe I'm not thinking right, but it seems like there are sort of constraints that it's like you're ignoring it, because how would going back to the first example with there's a parallel here, it seems like locally you can't know whether eliminating a particular connector is the best thing to do.
Yes,
And
that's right. So what I'm going to get to are local rules for exactly for that. So the way I've talked about so far is that we construct some giant cost function, and it depends on all the conductances of all of these edges of the network, or all the spring constants, everything. I have to know all of the microscopic details in order to construct that cost function, and then do gradient descent on it. Okay, and what I'm going to get to is a way to get around that. Yeah, that's exactly right. So the brain actually uses neurons to do that. Helps with this computation of how to dilate and blood vessels. All right, so the flow networks are really just a simple sort of scalar version of the mechanical network. So how are we going to do this? All right, so there's actually a healthy community of people that take folded proteins and convert them into spring networks. Okay, we're not going to do that. That's not what we're doing. Okay, we're doing this. We start out with networks. We just happen to have networks for jam packings lying around. And so we took our networks from jam packings and we started working. And then the idea was we're going to design these networks to have allosteric. Okay. And we can turn them, they can be mechanical networks if we put springs there, or they can be flow networks if we put little pipes there. Okay. So this we started with the same kind of networks, turn them into either mechanical or flow networks. And then the idea was we're going to tune this allosteric function into we got a whole ensemble of networks, and we're going to tune the same function into each one. All right, so how do we do that? Well, it's the same old way, right? You have constraints, and my constraint is, I'm going to start with an inequality constraint, sort of like jamming, which is that the target strain has to be at least delta relative to a source strain, which is 1. Okay, so I'm going to call the source strain 1, and then I want my target strain to be at least delta. And so I'm going to construct a cost function, which penalizes me if my target strain is less than delta. Okay, and then I'm going to tune my learning degrees of freedom, which are the presence or absence of a bond, or the bond stiffness, or the equilibrium lengths. Okay, or if it's a flow network, the conductances, in order to minimize this cost function. Okay, so I just do gradient descent. And it works. So here is the network. This is with periodic boundary conditions. I have 2D ones so you can see them, but we do this also in 3D. And so here's my source edge. So I'm putting a strain, which I call 1 on the source edge. And this is the initial strain across the target. Okay, it's much smaller than the source. And now I'm going to start tuning by gradient descent. Okay, and as I change the stiffnesses of my springs, the target strain just goes up and up and up. Okay, until I reach the desired value, which in this case is 1. Okay, so I did it. These blue dash ones are springs that effectively get removed entirely. Okay, and here's a flow network. So I start out with a pressure drop, which I'm going to call 1 at the source. And I want to tune my target pressure drop across this edge to be 0.2. And you see it starts out very small. Okay. And now I'm going to tune the conductances of the edges. And as I do that, again, the blue dash ones are the ones that effectively get removed. These pluses and minuses give you the signs, and the size gives you the magnitude of the pressures on the nodes. And you see that eventually it does reach the desired value. Okay, so so this is great, right? We can do it. Very happy to write a paper. Okay, but the problem is that it's great on the computer, but this is totally useless for materials, right? Why? It's not scalable, and the real problem is that we have to know every single detail at the microscopic level in order to construct the cost function and then do gradient descent on it. That's a very complicated, not very scalable calculation. Although, of course, that's what you do on a neural network all the time, artificial neural network all the time. But not only do I have to know everything and do great to figure out what direction to go, what to do gradient descent, but I have to be able to go in there and make those little microscopic changes. I need a little edge demon in there to make those changes for me. And if I have a block of material, I can't do that. I can't send in a little thing. Well, David can, but most of us can't send in a little thing and just, modify these things the way we want. So, so that's the problem, right? The minimizing the cost function is inherently global. Doing gradient descent on it is a global thing. That's exactly what Glennis was getting at. And that's a problem. Okay. So what can we do? Can materials learn how to function without having these little edge demons, and without having a central processor to calculate the cost function and the gradient? So here's now where I start that song and dance that I was mentioning to David's, in response to David's question, which is that, right, we actually, that's not what we did. What we did at first was not gradient descent on the bulk modulus. What we did at first, that was Daniel Hexner's brilliant contribution that showed that was actually the most efficient thing to do, and that we could really understand things well if we did that. But what we actually initially did, just following our noses with Carl Goodrich, was we preferentially removed the bond that was under the largest stress. If we were tuning the bulk modulus, if we put the system under an isotropic compression or expansion, we removed the bond that was under the largest stress. Okay, and that gave us almost the same thing. Not exactly, but it was actually also extremely effective in tuning the Poisson ratio to reach -1. And so what are we doing when we're doing that? In that case, the system is automatically adjusting the node positions for us. We didn't have to do any calculation. The system just minimizes elastic energy, right? And now, if I add some degrees of freedom, like just say, well, suppose my bonds, if they're under too much stress, they just break. Okay, then the bonds that are going to preferentially break are the ones that are under the greatest stress, right? And so if I apply an isotropic strength to this, I'm going to drive the ratio of the shear to bulk modulus up. I'm going to drive the Poisson ratio negative. Okay, and that's an aging process. In other words, I take this system, I put it under some strain, and I just watch bonds start popping on me. Okay, and the trajectory that the system takes under that aging process is directed by the stress that I've applied through my boundary conditions. And so this thing that I said, when you think about it, it just blows your mind away, because the idea is pruning the bonds under the greatest stress under the isotropic strain with that boundary condition is almost the same as pruning bonds that change the bulk modulus the most, right? That's what I said. So, but pruning the bonds that change the bulk modulus the most is doing gradient descent on this cost function, which is the bulk modulus. But the only thing that the system wants to do gradient descent on is the elastic energy. So in the aging process, the only thing, it's just physics. The system just wants to minimize elastic energy. Okay, so that's what it's saying is the cost function is really similar to the elastic energy when I apply the right boundary condition, isotropic strain. Okay, so and what is happening, right? Each bond is just saying, oh, I got over my threshold, I'm going to pop, I'm going to break. So it's a totally local rule. Each bond we don't have to know what's happening everywhere else. Each bond just responds to what itself feels.
This is not entirely true, because the stress of each bond is actually the result of.
That's what makes it work. That's right. The stress on each bond does actually depend on everything else, but physics figures that out for you. Each bond just has to make the decision, am I going to break or not?
The decision is local, but.
The decision is local. But exactly, that coupling, which gives you that stress in the first place, is not local, but physics is taking care of that for you. Right? We don't have to calculate anything.
You're not saying you arrive at the global minimum this way, just that you get very close.
You actually do arrive at the global minimum if you have enough degrees of freedom, if you have enough learning degrees of freedom. Yeah.
Do you have to pop things one at a time and let the strain redistribute?
You don't have to pop things one at a time. So we looked at what happens if I pop more than one. It's most efficient if you pop one at a time, but you don't have to just pop one at a time. And one thing we did not really look at is that you can get avalanches of poppings, and does that, that doesn't seem to ruin what happens as far as we can tell. Yeah.
What do you mean by an avalanche? Does that mean that the second bond breaks before the network recalibrates?
I'm just saying that when I pop this bond, it causes another one to break, that causes another one
Well,
to
wait,
break.
wait.
Yeah.
That's not anything different. Unless that's happening on a time scale that's before the whole network of refill breaks.
That's right.
And so that's what you mean by.
That's
that.
what I mean by now.
Andrea, does it ever happen that in a big system, probably does happen, two bonds happen to be at almost the same stress, and then randomness comes in, and then you have many different ways by which this process can develop.
That's correct. And there are many, many different routes to the global minimum. So that's the thing, that when you have a lot of degrees of freedom, so the point is, if you don't have very many constraints, okay, and you have a lot of learning degrees of freedom, then just about any route you take will eventually take you to the global minimum. It's really, really easy to get to the global minimum, and we're counting on that by having a lot of, and that's the regime that you work with in machine learning too, with the deep neural network. You make it huge so that you have a lot more degrees of freedom than constraints. Okay, so I just want to show you that it actually works in the lab. Okay, we're not just making this up. Well, we were just making it up, but it turns out to work. So this is Nidhi's work. Nidhi Machine, who's now postdoc at MIT, was a student of Sid Eagles at the time. So she took a jam packing and she laser cut the network that you would derive from it, okay, out of a solid foam. Then she took this and she put it in a frame, and I forgot to bring it with me. She gave me a beautiful. So you see, you take this thing, you put it in a plastic frame that's a little smaller than your network. So you compress it, you wait for an hour. Okay, it initially has a positive Poisson ratio. You wait for an hour, and okay, the Poisson ratio goes negative. Now this is as a function of the strain. So it's a function of the size of the frame that you put it in. So the smaller the frame compared to the piece of foam you started with, okay, the more you go this way. So what you see is that if your frame compresses it enough, and you wait for an hour, eventually the Poisson ratio does actually go negative. And so what's happening, right, is the regions that are under the greatest stress in this network are deforming the most. That's all you need. Okay. So this nature is doing the work for you.
Can I ask a question? I don't know if you can hear
Yes.
me. This is Alex Donev here.
Yeah. Hi, Alex.
Hi. When you, so what you call here Poisson ratio is you let it sit for an hour, and then it reaches some sort of steady state where you can remove the frame and then it doesn't go back to expanding.
Correct. You remove it from the frame and then you measure the Poisson.
Okay, so
ratio.
it's so plastic that eventually it just adjusts to the new state. Okay.
Correct.
Thanks.
It's possible that it then re-expands, the system readjusts after time, because, but we're working on time scales that are slower than that. But it is mostly plastic deformation as far as we can tell. All right, so then Daniel Hexner, very worried about safety on the road and doesn't like people driving while they're aging, came up, actually, I guess he likes it, came up with this really nice thing where instead of putting it just in a frame and waiting, okay, what you do is you take this thing and you compress and then expand and then compress, just do cycles of compression expansion. Okay, and that's actually even more effective. And so, so I'm going to introduce some language now. Okay, so the idea is I'm going to apply my source strain. So if I want a Poisson ratio of -1, okay, I'm going to imagine applying my source strain, which is that I just compress the system this way. Okay, and I'm going to apply what I call the clamp condition, boundary condition, where I apply that source strain and then I apply the desired target response. In other words, if I compress this way by this amount, what I want to have a Poisson ratio of -1, I want this dimension to compress by exactly the same amount. Okay, so what I'm going to do is I'm going to compress isotropically by that amount. Okay, So I'm going to apply not only the source, but the desired target. Okay, so that's what I'm going to call the clamp condition. And then he said, okay, let's just do gradient descent with our learning degrees of freedom, which in this case were the equilibrium lengths of the springs. Okay, so we just do gradient descent of the energy with that boundary condition, and as we do this, so we drive isotropic compression expansion. Okay, and so what we're doing is we're lowering the elastic cost along that trajectory. Okay, and so the idea is, right, it's, as I said, the elastic energy with that condition, that desire, where I apply not only the source, but the desired target value, is my cost function. And that's what I'm minimizing. Okay. And that works. Okay. So here's the Poisson ratio. Starts out like this, function of strength. Okay. After I've gone through a lot of cycles, okay, it reaches this value of -1, very close to -1, okay, over this range of strain. And what determines this range of strain? Aha, the range of strain over which it's -1 is the range of strains over which it was trained. Okay, so if I go isotropic compression to expansion over this tiny little range, okay, it gets low over that small range. If I do it over a bigger range, the green dashed ones, okay, it's -1 over that bigger range. And if I do the red range, -5% to +5%, okay, then it's close to -1 over that range. So the system remembers the strain at which it was trained. Okay, all right. So what else do I want to say about that?
Andrea, can I ask another question?
Yeah.
So there's no free lunch, right? So as the material is optimizing this specific property, do you have some idea what it's giving up, like what actually happens to it?
Yeah, it might lose other properties, right? So for example,
Like, is it
suppose,
becoming weaker? Are G and B becoming weaker? The ratio is adjusting, but they're becoming.
yes, they
smaller.
are becoming weaker in this case.
Okay. Mhm.
Yes, they are.
Andrea, I'm sorry, you may have mentioned this. In the unaged system, does it have to be any particular structure? Could it be like a regular array to begin with?
Yeah,
And it
Yeah.
could also be like, I don't know, some random network?
it could be some random network, it could be periodic, which is a tiny epsilon of disorder to break the symmetry. But yeah, it will very rapidly adjust itself to the same thing.
But if you took the crystal and you did that, as you said at the beginning, it doesn't change.
That's the perfect crystal. If I just
Yeah, yeah, I'm
add
saying. the perfect crystal.
infinitesimal amount, a perfect crystal is a
Yeah.
special point. That's right. All I need is an infinitesimal amount of disorder, then I'm on my way.
And you might be about to tell us this, but after you've blown the bonds, is the remaining network, does it have some sort of like properties of hyperuniform or something like that?
No. It is not hyperuniform. And it doesn't have to be. In fact, there's almost no change. So what I didn't say was that, for allosteric, okay, for a network of about 1,000 bonds, okay, which is a reasonable protein, maybe size, maybe small compared to protein, but so for a network of 1,000 bonds in 3D, I can successfully tune in allosteric about well over 99% of the time. But how many bonds do I have to remove in order to get it? On average, 5. Okay, so the change of structure is undetectable, really hard to see. And I think, I don't know, if I were thinking about this in terms of a connectome for my system, right? Just knowing the connectome, if there were any error in it, I might just miss the function altogether. I'm not saying that has any consequences for the brain connectome, but for this connectome,
Can you
it
tell us
really
what
is.
a connectome is?
Oh, just if I knew all the deep, which one was connected to which, right? Just a small error in that, since I only had to remove 5 bonds to get this. If I had a small error of 5 bonds, I might miss the function altogether. If it happened to hit the crucial ones.
So this means that if I take sort of any sort of lattice, I could make a pantograph, for example. I could make a device that sort of copies what I'm drawing by just like punching out 5 bonds or
On average
something like that.
for allosteric.
That's good.
It's really tiny. Okay,
But it's not, that's not true for Poisson ratio, right? It's not completely tiny like it is for allosteric, where you just,
it's not completely tiny, but it actually, the scaling is really good. The scaling, we don't know the scaling exactly, but it's roughly linear in the length of the system, in the system length. So not L to the D, but it scales like L. So it's pretty good for, pretty good scaling for that. Well, I might know, it might be L to the D minus 1, come to think of it. It makes more sense if it was D minus 1. Okay.
but,
All right.
but
Oh.
allosteric is not a bulk property, whereas the Poisson ratio is.
Poisson is a ratio is a bulk property.
That's right.
So allosteric is a collective property, but not a bulk property. So so here's tuning allosteric while driving while aging. So what Daniel did was, here's my source bond. Okay, here's my target bond. Okay, and I'm gonna just go like this, or I think he did the opposite, which I have trouble. I'm such a klutz. Okay, but so you're driving both the source and we're driving the target with the desired response. Okay, and then we're adjusting the equilibrium lengths to lower that elastic energy. Okay, and then every so many cycles, we pause and we do a readout cycle where we only apply the source. Okay, and we look at what is the target response. And what you see is that over time, the source is this green, it's just going strain, the green just going up and down. Here's the response of the target, and it just goes up and up and up towards the desired value to be the same as the source. Okay. So the system is successfully tuning allosteric. So this is great, right? We can go in there and do that in principle, right? Yeah, and we didn't have to know anything about the system in order to do that.
I don't mean to interrupt, but am I seeing it correctly that it feels like most of the bonds that are like breaking and being added are at the edges, or?
So bonds that are affected tend to be closer to the source and target. But this is actually something that we've spent a lot of work on. And we've actually developed persistent homology analysis to understand what are we doing when we change these bonds. How does changing these few bonds actually give us this collective response? And it turns out that we get an answer from persistent homology, which says that the system actually breaks up into sectors of nearly uniform strength. And that's what these sectors, the difference of this strain, if I treat these sectors as rigid bodies, the difference in their strain is what gives us the allosteric.
I see. So most of the changing or the aging that's happening is near the targets.
Well, it's sort of distributed sort of on lines that connect the source to the target, so that it on the boundary of a sector.
Yeah. Could you pick
Yeah.
2 target sites and tune them simultaneously?
Yes. Yes. In fact, so what we did was we said, okay, let me just we did this simplest case, just a single source,
right,
and just ask how many targets could we tune simultaneously? And what we found was hundreds. Okay, in other words, in a network of 1,000 nodes, we could tune actually about more than 200 sites to have allosteric. Okay, to have a response of order 1. And so just tuning one site to have allosteric, one target, is trivial. That's what I'm saying. So that's the limit. The limit is several hundred, and to tune one allosteric response is so far below that limit. That's why it's so easy, and that's why we're so successful. Yeah.
Do you have specificity constraints when you tune several like allosteric responses? Like if you light up one, it only lights up another, but not like the other.
Oh, yeah, we can do that too. We can do a sort of a transistor thing. So, yeah, you can have this thing and it lights up this one, but if this one is on, then it doesn't light that up. You know, we can play all kinds of games, or we can do source target pairs. We can just say, when I do this one, it does this one, but no response over here. When I pinch over here, I get a response here, but not over here.
Yeah.
No problem. These are all just, they're just extra constraints.
Yeah.
And again, if we have enough degrees of freedom, we can satisfy those constraints.
There must be some limit, right? You couldn't have two
Exactly.
basic bonds
There's a
have
limit.
opposite allosteries.
Correct. That's the, and so for that one case where one source and targets, that limit is what I told you. It's,
But even if you just had two targets, right, there must be some, like if you put the two targets close enough together and have them do opposite things, that there must.
yes, that's right. That's right. So, so what we were looking at is the random constraint satisfaction transition. If we just choose things randomly, where does it end up? And that's the answer. But there are always exceptions. That's why the success in tuning allostery, even just one target, is not 100%. It's a little shy of 100% because of special cases like that.
And the solutions aren't unique. There are many
So
different.
there are many
solutions.
different solutions for the same target.
Right.
And source. Exactly.
And to follow up what Alex was proposing, I guess what's lost is as you tune the system, as the system tunes itself to solve one problem, you lose the flexibility to tune it for another problem later.
Okay, in this case, but we'll get to a case where that's not true. It's, yeah.
But can you
If your
also-
bonds can get stronger as well as weaker, then that's not true.
Can you also do it by adding the ones?
Yes,
In which case you wouldn't have the problem.
and in
that
which
Alex
case you
said.
wouldn't have the problem of getting weaker. That's correct.
Yeah.
Or you can say, every time I take a bond away, I add it
Yeah.
somewhere else.
Right.
That's right. That works as well. These are all acceptable degrees of freedom. We just looked at the ones where we took things away or we, yeah. And I have to say, in this case, right, it doesn't necessarily, in this case, it doesn't necessarily get weaker because the equilibrium length, we got this rule that if I stretch it, the equilibrium length wants to get longer, but if I compress it, the equilibrium length wants to get shorter. That's what we're doing. That's what Daniel Hexman is doing. Okay. Okay, but there is a problem. Okay, it turns out that directed aging doesn't always work. And it works if you're near the limit of mechanical stability. So if you have a very sparsely connected network, so that on average, the number of springs connected to each node is not too far above twice the dimensionality, or 6 and 2, 6 and 3. And so that's why there are long-range correlations between the source and the target. Okay, and what Daniel did to get around that was to add repeaters in this. So I'm going to take repeaters. So I'm going to choose randomly some bonds in between here and start oscillating those as well. Again, that works. Okay, but if you try, for example, to apply to flow networks, where the limit of stability actually is 2, because it's like a one-dimensional problem. So it's 2 times dimensionality, it's just 2. Well, 2 just gives you a straight line, right? So any network is going to be well above it. And so it didn't work at all. Okay, so that's not, he discovered it. He couldn't tune flow networks that way. All right. So Naki came up with this other thing, which was inspired by ideas from neuroscience and machine learning, which is contrastive Hebbian learning. So the idea in equilibrium propagation. So the idea is the following. So the cost function, right? What we're doing is we're saying, if I just apply the source and I don't do anything to the target, if I just apply the source, what I want is for the target to have the desired response. Okay. And the clamp is I apply the source and I apply the desired target response. And so the cost function that we usually use is the free case minus the desired response. I want that to be 0. I want to minimize that square. Okay. But instead, I could look at the difference between free and clamped. That's the same thing if I clamp the desired response. Okay, I want to minimize the difference between the free and the clamped. If I do that, that's exactly the same thing, right? Because I've chosen my clamp to be the desired response. And so, so then it comes down to comparing what happens with two different sets of boundary conditions. And that works. Okay, so that's what I said here, I guess. The original cost function was enforcing the free response should be the desired response. Our new cost function is going to be is the clamped response, which is clamped to be the desired response, is the same as the free response. And so I can write down these equations, and because the elastic energy is the sum over edges, okay, when I differentiate with respect to a property of an edge, it's a local rule. Okay, so this is a way for any cost function you want to construct. Okay, if you do this contrastive thing, here's the rule. Okay, and the implementation of the rule is the same. It's just this, take it with this boundary condition, take with that boundary condition, and do gradient descent. Local. Okay, and it turns out that in the limit that instead of applying the desired response instantly and say, I want free to be desired, I just gradually nudge it. So I apply a target response that's somewhere between what I have and what I want. Just nudge it a little bit. And if I nudge it a little bit at a time, and the limit of infinitesimal nudges, this is actually equivalent to gradient descent on the cost function. It's guaranteed to work in the limit of infinitesimal nudges. Okay, and just to say, what is directed aging? Directed aging is just this. Okay, so if the free, so you can see directed aging is not necessarily guaranteed to minimize the cost function. If you minimize the cost function, we need this extra term. Okay, but there are cases where this extra term is not so important, and that's if the source and the target are highly correlated. Okay, so, and this works. You know, we can do allostery in both flow networks and mechanical networks. This is on the computer. This is the error. So as you let the system go over time, the error goes to 0. So you manage to get what you want. For allostery, we classify the zeros and ones, handwritten zeros and ones with these networks, and that worked. Okay. But what we want is to do it in real life, okay, not on a computer. Okay, and this is where Doug and Sam Dillard come in. Okay, because here's the problem, right? So here's what we want. So the conductance, this is now, it turns out flow network, flow network with pipes and conductances in the linear regime is exactly the same as an electrical resistor network, right? So they built an electrical resistor network where these edges have variable resistances, okay? And here's the first prototype. Okay, 16 edges, 9 nodes. And this thing learns. It's so cool. Okay, so the idea is the following. So coupled learning, right? What is coupled learning? Coupled learning says, okay, in this case, I want to change the conductance of edge J, okay, to do gradient descent on the difference between the power, if I apply the clamped condition for the target has a desired response, minus what I get with the free, right? All right, well, the power is just V squared times the conductance, right? We know that for the edges. So when I take this derivative, this is just the difference of the squared voltages on that edge. That's the local rule. The change of conductance only depends on the voltages across that edge, but under two different sets of boundary conditions. And so what they did was they simplified it further and just said, well, we're just going to step the resistance up or down depending on the sign of that difference. Okay, so they didn't actually implement the coupled learning rules, they did this approximation to it. Okay, but the really hard part, right, is to, what's next? Oh, yeah. The really hard part is how do you compare two different sets of boundary conditions at the same time? right? You can't apply to different boundary conditions at the same time, sets of boundary conditions at the same time. So what they did, which I think is just fiendishly clever, is to make two copies of the network. Okay, identical copies of the network. And now each edge is actually this pair of twins. Okay, this pair of edges. One network is running the free boundary condition. The other one is running the clamped boundary condition. And then there's circuitry on each edge to couple the two twin edges together and compare the sign of the voltages. Okay, and just then tune the resistance up by one notch or down by one notch. Okay, and this thing works. Okay, so
Can I ask a question, Andrea? Sorry.
yeah,
What is the clamp? Like, what is the goal? What is the clamp means you want to achieve a certain voltage at an output node, or what is it?
it depends on your task. So let me go through it for this iris data set.
Okay.
Okay, so this is a famous data set of irises where they take 4 measurements of the iris. Okay, and then they do this for 3 different species. And then based on these 4 measurements, the idea is to sort the irises into these 3 different species. Okay, so here we have 4 inputs, these red things plus ground. Okay, and then we have 3 outputs, iris species 1, species 2, species 3. Okay, and so so it's the voltages, right? You feed it these 4 voltages that are determined by these measurements, these sizes of the sepals and petals. Okay, and then it spits out 3 voltages, and you want this one to be large, or that one to be large, or that one to be large, depending on which species you've got. Okay, and here's the error, the classification error. It starts out high and it goes down. It achieves a classification accuracy of 97%, which is comparable to linear classification methods.
Shouldn't it start off at 67%? Error.
Start out, if it were just totally randomly sorting them. Yeah,
Yeah.
so this depends on how you choose your targets. So they actually did a bit of a cheat here. Well, not a bit of a cheat, but the target is not exactly this one lights up or that one lights up or that one lights up. We start with something, okay, and for the first trainings, we just say, okay, let's take the what we get for this species and the linear combination we take for this species, and then I'm going to call that species 1, and the other one species 2, and that's why it starts out lower than 67%. Okay, so here's the thing. I think somebody asked about this, which is it adaptable? It's Alex, I think. Can it learn new things? And this just shows this network can learn new things. So first, we teach it to do classification. And we say, no, I want you to learn allostery. Okay, so let's make this ground. Here's our source, 1 target, 1 source, 1 target. It learns that. Okay, they say, no, why don't I have 1 source and 2 targets? It learns that. Okay, 2 sources, 3 targets, learns that, etc. And we keep teaching, and then we say, oh no, actually, I want you to learn how to solve 2 equations and 2 unknowns. 2 different problems. It learns how to do those. The interesting thing is to say, okay, now go back and learn this one, and it finds a different solution where the resistors have different values, right? Because there are many solutions for a given problem. So this thing can just learn one task after another. Yeah. Let's see. Yeah, go ahead.
Why is the error going up after a certain point? Is that a sign of overfitting?
Oh, why does it go up here?
Yeah.
I think that's noise.
Oh.
Yeah.
Because that's the log scale.
Yeah, this is a log. Yeah. Yeah. Yes.
Is it purely mechanical, the resistance updates? There's no like little circuitry, I don't know, like the
There's circuitry.
informatics.
There's your circuitry that says, I want the resistance to click up if the sign of the voltage difference is this, if it's that. It's gonna click
Just
there.
like robotics.
Just, I don't know what. Is it robotic?
There's nothing mechanical, it's all electronics.
Andrea, what does this have to do with Hebbian learning?
Because what I'm doing is I'm minimizing the difference between free and clamped. So I'm comparing these two cases.
Okay.
That's what the contrastive aspect. Yeah, you had a question.
Yeah, so the regular neural network that does this, how many nodes are like, how does it compare to this?
To a neural network? Actually, I don't know. We didn't try that. Good question. We did not check that. Yeah. You know, this is a linear case. It's purely linear, and so it's not as powerful as a neural network of the same size, probably. Yeah. Okay. So that's what I want to emphasize, that the learning rule is the same, right? What changes is just the boundary condition for new tasks. And that's why we can teach this old network new tricks. Okay. Finally, I just want to make the point that it's incredibly robust to damage, right? Just like you can remove half the brain and somebody can still function, right? Obviously, this is, but you can't do that to an iPhone. You can't remove half the iPhone and expect it to keep working. But in this network, okay, we could take away 5 out of the 16 bonds, and it could still each time successfully learn allostery. So learns allostery, clip this bond, so learns it again, clip that one, learns it again, clip the purple bond. It had no effect whatsoever, didn't even have to retrain it. Clip the green bond, okay, and so forth. And so, so this could withstand like damage to about 1/3 of the network, and it could still learn. So, and that's because it's fully distributed learning. There's no central processor, right? Each edge is learning on its own according to this local rule. So physics is doing the forward computation. Physics is saying for a given set of inputs and a given set of resistance values, here's the voltage of the target, right? Physics is doing that for us. And then instead of back propagation to say, how do I adjust my resistances? Oh, let me minimize this cost function. What we're doing is we have that local rule. It's completely distributed. So we're excited about this. And it turns out that just by the time we just increase our network by about a factor of 10, the size of our network by a factor of 10, and speed up the speed of it by a factor of 10, will already be outdoing solving coupled learning on the computer. Okay. And with modern electronic manufacturing, we can speed up so first of all, our fantastic colleague Mark Miskin already figured out how to speed up the electronics by a factor of 1,000,000. Okay, with modern electronic manufacturing, we can scale up the number of nodes easily by a factor of 1,000,000. Okay, and by then, according to our estimates, we might be within striking distance of competing with artificial neural networks on the computer. Okay, because of the incredible scalability of this, and it should use much less power. Okay, so now my friend Sid Nagel has what he calls the bullshit line. So everything up until now, I hope we have something to back it up. Okay, now I'm descending into pure bullshit. Okay, I'm below the bullshit line. And so I think one really interesting thing is, for example, the cellular cytoskeleton. This is something I'm sharing a postdoc with John Parker to look at this. Is the cellular cytoskeleton a learning machine, like our thing? And why? Because, for example, the network of actin filaments, it has crosslinkers that come on and off in response to stress, right? If the node's under too much stress, the crosslink is just going to come off. So this is something that can change its network topology in response to stress. The actin network is also very close to isostaticity, so very close to marginal mechanical stability. So directed aging should be enough. Okay, so is the cytoskeleton changing its mechanical responses constantly by changing its network topology in response to these very complicated stress states that it's under? Maybe it's a learning machine, maybe it's learning things. Okay, same thing with collagen, which makes up our extracellular matrix. Okay, So, and then, as I told you, we can tune in a protein size object, we tune hundreds of sites to have allosteric. Okay, but you don't ever see more than a few sites that are allosteric. At most, usually just one. Okay, so real proteins are operating well above the limit of how many targets they can have, how many allosteric sites they could have. And so again, this is surrounded by a bullshit line. Oh, maybe that's why so many proteins have managed to evolve allosteric, because as we found out, when you're well below that limit, it's really easy to do it. You hardly have to change many bonds at all in order to get it. And you're successful almost all the time. Okay, so maybe that's why it could have evolved.
But your largest degrees of freedom in this case is only the sequence.
That's right. But I have 21 choices of amino acids to put there.
But
yeah, those are my learning degrees of freedom.
But you don't have a goal. It's not like you take a protein and you sit there and you say, I want this thing to bind when this thing binds. So I'm going to
Correct.
shove this in here.
It just happened by accident, by natural
Yeah,
selection.
So the most this can do is maybe tune the system once it's already achieved the basic thing. It's a nudge.
That's right.
But this can't be a way that it develops allosteric in the first place.
But there again, I'm descending below a bullshit line, but we're starting to talk to Kendall about that. Maybe it's something that we can do on a computer to design proteins to have allosteric.
Sure, you could use a computer.
We can use it to do it, of course, but the point is that if it's not so hard to get allosteric, maybe you could have done it just by random mutations in natural selection. Right? If you had to change a whole lot of things, in fact, Ken Dill just 2 weeks ago at the Gordon conference just was telling me that there's this creationist who goes around and says, he uses allosteric as an example of why we must have, intelligent design, because how could you possibly get allosteric, right? But actually, if it doesn't take too many changes to get it, and you think, oh, I could have allosteric anywhere, right? Then maybe it's conceivable. So that's what I'm saying. So, so really excited about coupled learning. One question is, can we apply to other kinds of networks? But before I quit, here's my last advertisement. I've been very concerned over investigations of Chinese scientists over research ties to China. The Justice Department under Trump started this China initiative to investigate scientists at universities and in industry. And overwhelmingly, the ones who are investigated are Chinese. And the Justice Department hasn't stopped doing that under Biden. And so a bunch of faculty at Stanford put together a letter to Merrick Garland asking him to end the China initiative. Actually, recently, 20% of the faculty at Princeton signed on to that letter. It's open to all faculty now, faculty and staff. Okay, I'm sorry, not students and postdocs yet, but faculty and staff. So I urge you to think about signing this letter. Give everybody a chance to pull up their. Okay, and then I just want to thank the people who actually did the work. On the next slide, as soon as is everybody done? Okay. Thank the people who actually did this work and my fantastic collaborators, all of them, and the people who gave us the money. Thank you.
Are there more questions?
You're using an electrical network right now. Is that the most energy efficient network? It's probably the easiest to build, but is that the most energy efficient you can come up with, or like?
It's not necessarily the most energy efficient. That wasn't the goal, but it does have. It's actually it's fairly simple.
Yeah.
Much more simple than having a simple processor to do machine learning calculations on the computer. Yeah, I mean, it's a question, can it be even simpler? But this is just the first design. Now the second one, which doesn't have a global clock, then we've got the third generation, this Mark Miskin's thing where he speeded up the whole thing by a factor of a million. He's amazing.
So you showed us something shiny and great. That means I want to break it.
Thanks, David.
So suppose I replace, I think if I replace the resistors, which are ohmic, with light bulbs, which are nonlinear, it will still work.
Yes,
I think
it actually should work better. And in fact, Mark's circuit design is easy. It's easy to make a nonlinear. It is actually not. It's linear in a certain regime, but
So can I break it by making it non-local, by having like all-to-all bonds? Does that break it or does that make it
doesn't
better?
break it. Because each bond still responds to what it wants to do. It just means that you have to, there's more
One has to
tuning
be zero.
involved. It's just not very efficient.
Okay, now I'm going to keep going.
Yeah.
Imagine that each node, instead of just being a Kirchhoffian node, imagine, for example, it has some rule like it sends the current off to the left or something like that. You know, can I break things by introducing topological constraints at the nodes? Or would I make it better? Or should that be a conversation over drinks?
That should probably be a conversation over drinks, and that it's a bit of the same thing that goes into if we wanted to tune biochemical signaling networks and stuff, with this issue of directionality. So, you know, these things, what this does this is the same as what this does that, right? And you know, if you break that symmetry, we haven't looked at what happens. But I don't think that should kill. I mean, it doesn't. The brain.
There are other questions. I think we should thank you.